All right, today we're going to dive deep into a really fascinating piece of theoretical physics. We're talking about a force tensor from a framework called UPT, or Postmodern Unified Theory. And we're going to break down how it describes the forces inside a system in a completely, and I mean completely new way. So let's kick things off with a huge challenge. Imagine you had to describe every single internal stress and force inside an object. But here's the catch. You're not allowed to use any information from the outside world. No external maps, no pre-existing fields, nothing. Just what's inside. How on earth would you even start? Well, that's the exact problem this UPT force tensor was built to solve. At its heart, the force tensor is a mathematical object that does just that. It describes the internal state of stress and energy. But it's not just some random equation. It's built on a super strict set of rules from the UPE framework, something called the Bo-Trithuk Nentam, or FBK for short. You can think of the FBK as the constitution of this theory. It dictates how every single part has to be built, right from the ground up. So to really get our heads around this, here's our game plan. We'll start with the core idea, then look at the guiding principles, the rules of the game. After that, we'll deconstruct the math itself, see how it's put into practice, and finally, we'll tackle the biggest claim of all, that this whole thing might be unique. Okay, first up, the core idea. Before we even touch an equation, we need to understand the one single ingredient this entire theory is built on. And here it is. That ingredient is called mass intensity, which we'll just call M. Now, what's really key here is what this isn't. This is not your high school physics density, which is just mass averaged over some volume. No, mass intensity is a point value. It's the concentration of mass at an infinitely small point in space. The entire theory, everything we're about to see, is built from the single number and how it changes from one point to the next, its gradient. Now, let's talk about how you build with that ingredient. You see, you can't just cook up any old equation you want. The UPT framework has these 5 foundational principles that act like guardrails, strictly controlling what the final force tensor can look like. These are the rules of the game. And here are the 5 big ones. First, it has to be FBK internal, which means you can only use mass intensity and its gradient. That's it. Second, there's a hard line drawn between the physics deep inside the material, the bulk, and what's happening on the surface. Third, it absolutely has to conserve energy. Fourth, it has to be isotropic, which basically means the laws of physics don't change just because you turned your head. And finally, the results you get can't change if you decide to measure mass intensity in different units. Now, of all those rules, that first one, the FBK internal principle, is by far the most powerful. It's the most restrictive. It forces the whole theory to be completely self-sufficient, building its entire picture of force and energy using only what the system itself provides. And this quote from the source material just hits the nail on the head. It says it all. You can only use the mass intensity field, I, and its gradient. You are forbidden, absolutely forbidden, from importing outside geometry or fields from other theories. Everything, and I mean everything, has to be built from scratch, from the inside out. Okay, now for the part you've probably been waiting for. Let's get into the math. But don't worry, we're going to crack this thing open piece by piece so you can see exactly how those principles we just talked about literally sculpt the final equation. So here it is. This is the equation for the force tensor inside the bulk of the material. And this formula wasn't just pulled out of a hat. It is the direct mathematical consequence of applying those 5 guiding principles. It's the only thing that could come out of that strict inside-out building process. Let's break this down because it's actually got 2 main parts. The first chunk on the left, that's the anisotropic part. You can think of this as a directional stress. It cares about the specific direction the mass intensity is changing. The second chunk on the right is the isotropic part. This is way more like uniform pressure in a liquid. It pushes or pulls equally in all directions, no matter what. So what's the missing link here? How do we connect this abstract math to a real material, like steel or water? Well, the answer is in those 2 little functions you see, a of I and b of I. These are the material functions. They hold all the specific secrets about the substance you're studying. To make this theory do any real work, you have to figure out what these 2 functions are, using actual experimental data. The theory also makes room for this optional asymmetric piece called T_DC. It only shows up under very specific circumstances, but the really important thing is that it's constructed to be gauge invariant. That's just a fancy physics term that means our physical predictions, the stuff we actually measure, don't change even if we mess around with the underlying math we use to describe them. It's a crucial consistency check. So we have the rules, we have the math, but how would a scientist or an engineer actually use this thing? Let's switch gears and walk through a practical workflow for how you'd apply this UPT force tensor in the real world. The whole implementation process follows a really logical sequence. You start with your data, the measured mass intensity field for your object. Then, here's the key step. You use that data to calibrate or figure out those material functions, A of I and B of I. Once you've defined what's going on at the edges, you can finally calculate the full tensor, figure out the forces, and then run a final check to make sure it all adds up and energy is conserved. Now, to make this less abstract, let's look at the simplest possible example they give us in the source material, figuring this all out for a simple one-dimensional bar. What's so cool about this slide is how it lays out the problem like a puzzle. In this 1D case, we know a bunch of stuff. We know the measured mass intensity all along the bar, we know how long it is, and we know what forces are being applied at the ends. The only things we don't know are those material functions, A of I and B of I. So by fitting our model to the data we already have, we can solve for those two unknown functions. This is exactly how the theory connects to reality. And that brings us to our final section, which honestly contains maybe the most powerful and mind-bending claim in the whole document. The argument isn't just that the force tensor can look this way, it's that given the starting principles, it must look this way. The claim is that this result isn't just one possibility, it's inevitable. The proof unfolds in 4 beautiful logical steps. First, the principle of isotropy locks the system's energy into a form that can only depend on mass intensity, I, and the square of its gradient. Second, you use a standard mathematical tool to derive our exact formula for the tensor directly from that energy function. Third, the bulk boundary separation rule acts like a bouncer, forcing any other possible terms to the boundary out of the main equation. And finally, gauge invariance puts a tight leash on any asymmetric part that might try to sneak in. And this quote just says it all. The source claims that if you accept those 5 foundational principles we started with, then this specific mathematical formula for the force tensor is the only one possible. It's not one of many choices. It's the only one that satisfies all the rules of the game. So we're left with this final, really provocative question. Most physical theories are built by trying out lots of different ideas and seeing what sticks. But this approach suggests that if your foundational axioms, your starting rules, are correct, then the math might be completely locked in from the start. So what does it mean for a physical theory to be not just a possible description of reality, but an inevitable consequence of its own internal logic? That's a pretty deep thought to end on. Thanks for joining me for this explainer.